So, very good evening to all of you who are connected to this lecture from all over the country. I hope you have assimilated and got a feeling of various aspects of the solar system, including our planet Earth, from the previous lectures. So, here we basically we are going to learn about the atmospheres of terrestrial planets. So when it comes to the solar system, anyway, most of you have heard that different planets are there in the solar system. And there are a lot of scientific questions, scientific analysis, where we need to understand the solar system as such. Now, in the solar system, we have our planets. And the first thing which comes to our mind is that whenever you want to study a planet, there are two aspects of that. So, planet is physical entity. You have the surface, this physical planet as such, where majorly people from geology background, they would like to study the geology of the planets, the surface processes, and of course it's a highly interdisciplinary field. Apart from that, some of our planets have this envelope of gas around it, which we call as the atmosphere. And of course, all of you are very familiar. We are living on planet Earth. And I cannot but overemphasize the importance of our atmosphere in terms of our life here, the phenomena of weather, climate. So it is something which is affecting to all of us, even in our daily lives. So therefore, it is important to understand the planets, the atmospheres of other planets, as we have understood it for Earth. And this is what has happened in the past several years. The information which we had for our own Earth, the atmosphere, we have propagated that to the other planets. So there are two aspects here. One is that whenever you have this atmosphere, it has a history of the past and it has an evolution. And many of you are familiar that how the atmospheres of various planets evolved. So that is a very vast subject in itself, and that is what I am not going to cover here in this lecture. It requires several lectures for that. So letting forego the history of the evolution of the planets, I will be talking of what is the current state of the atmospheres of various planets. And in that also, we have planets which have atmospheres, we have bodies which do not have atmospheres. So I will again concentrate on the terrestrial atmospheres, but just to give you a brief idea, and all of you know this, that we can divide our solar system into four basically distinct types of planets. And that is that we have these Jovian planets, which are the outer planets like Jupiter, Saturn, Uranus, and Neptune. And they have a atmosphere rich with hydrogen. And then you have the terrestrial planets, which are rocky surface, and they have substantial atmosphere, which we will look into in this lecture. And you also have airless bodies, which some of them do not have atmospheres, and some of them have. So you have a variety of evolution of these planets depending on their position in the solar system and actually how this process evolved. But overall, if we say that whatever processes are occurring in the atmosphere, they play a very important role in the evolution of these planets and vice versa. So basically, as I said, we will concentrate here on the terrestrial planets. And what you can see here, I've shown you certain images from the three planets. You know, the terrestrial planets is comprising of Venus, Earth, and Mars, because they are rocky planets and they have similarities in some aspects. And the first two pictures are interestingly taken by the camera of our own Indian Mars mission, the Mars orbiter mission. And you can see the difference. This is in fact for the Earth. It is the first image of Earth which was taken by Mon, and you can see the clouds and the so basically the atmosphere, all of you know for Earth very well. And then for Mars, what you can see is basically actually a dust storm, which could be seen during that time, and this we will come to in more detail later. And as far as Venus is concerned, this is a very beautiful image of a lot of data which has been compiled by a mission called Akatsuki, which has been launched by the Japanese space agency, JAXA, and it is orbiting the Venus, and it has studied various aspects of Venus. But what is shown here is the study on the atmosphere, and this is a composite view of what it would look like. So these terrestrial planets have similarities, differences to each other, and more importantly, we would like to understand because they were once supposedly to be like Earth-like atmosphere. So we would like to study what is there currently. Now, if you want to study atmospheres in general, planetary atmospheres, that is what I'm calling it. Usually, what happens when we say planetary atmospheres, it's mainly dealing with all atmospheres except the Earth, because Earth's atmosphere has a very rich history of the studies. So traditionally, you study other planets, but I'm going to cover all three of them. And what is it that we want to study? So as I said, the first scientific information which even a layman has is the weather. And everybody knows when it rains or what is the temperature, how hot and humid. So these kind of meteorological parameters, even a layman is familiar with. And everybody would like to know what is happening to the atmosphere, the environment, how the weather is changing, how the climate is changing. But in terms of science, when the scientific community wants to study, you can divide the entire domain of planetary atmospheres into three broad categories. So there are processes, chemical processes, which belong to the category of chemistry because they are chemical processes, and because it's a gaseous envelope, the atmosphere, and there are various species, so they are interacting with each other, and so lots of chemistry is there. And then you have physical processes, and these physical processes are basically fall into various domains where you could have, for example, the absorption of the solar radiation into the atmosphere, and that would lead to various phenomena, which I will discuss on. So that those kind of processes are clubbed into something called radiative processes. So radiation is an important part, which is basically actually coming from the sun, and that is the major source of radiation which comes to each atmosphere, the atmosphere of each planet. And then there could be processes, as all of you know, the movement, the atmosphere is nothing but a gas, so it's a fluid. So there is the movement of this fluid, and that is in terms of winds and the motion of this atmosphere itself. And that could be at various scales. And all of you are familiar with winds and the smaller scales where you are having a seashore, you have a sea breeze, or you have longer scale circulations. Our country is experiencing the southwest monsoon, which is larger scale circulation. So all this comes under the purview of dynamics. So basically, if you see, the entire study of planetary atmospheres involves a lot of physics and to some extent a little bit of chemistry. So just to give you an overview again of the composition of various planets, that is the first thing which comes to our mind. That since it is it's a gaseous envelope which we call the atmosphere. What is the composition? And all of you know that in the terrestrial planets, it is the Earth which is rich in nitrogen and oxygen, and this is the oxygen which 21% which makes our life possible on Earth. And then you have the other two planets, which are Venus and Mars, which, for example, which have a very rich CO2 atmosphere. So the atmospheres of Venus and Mars are dominated by CO2, approximately 95.6% each. But you do have amounts of oxygen and nitrogen in smaller quantities, and we'll come to that later. So this is the broad distinction between the terrestrial planets. And as I said, the other planets are mainly rich in hydrogen. So this is a very rough overview of the composition of the planets and how they look like. Going into the detail of the terrestrial planets, you can see these three planets highlighted here as a pie chart, the composition, distribution, and as I said, you can see clearly the CO2 rich uh, atmospheres here in Venus and Mars, and the nitrogen and oxygen rich Earth atmosphere. So this is the major composition of these three planets. And as I said, there are small, there are chemical constituents which are very small in concentration, which sometimes we call trace gases because for Earth and even other planets, they are so small that you would not like to talk in terms of percentage. If you look at this, so we talk in terms of mixing ratios. And since they're very small concentration, we call them trace gases. But sometime later, I will show you that it is these gases, which are very small in concentration, which really impact the climate in some sense. And if you see, for example, for Earth, just to give you an example, the CO2 is very small compared to the overall composition. But you know the way it is impacting, especially in terms of the global warming. So this, as I said, when we talk of the atmospheres, the first thing you would like to know that what is its composition. And this is what is there for the terrestrial planets. And over the past several years, the past century, I would say, there have been a host of measurements in situ from the ground for other planets and also orbiting satellites, which have measured many of these concentrations in very great detail. So we really know what the composition of each of these planets is. The next question which comes when we are studying the atmosphere, apart from the composition, is what I said initially is the radiative processes. So as I said, the sun is the major source of radiation, which is giving energy to the atmosphere of any planet. And this solar radiation, as all of you know, comes in various wavelengths, and electromagnetic spectrum is there. Many of the students who are from physics would know this. And it is, all of you also are familiar living on Earth that many of these wavelengths, the spectrum of the electromagnetic radiation is shielded. For example, ultraviolet and the harmful radiation is shielded much earlier in the atmosphere of Earth. So basically, the radiation is coming in all wavelengths, but the major source of this radiation is the sun. And this is what leads to the temperature of the planet, the temperature of the planet as well as of the atmosphere. So this is a very simple sort of explanation which can be given that all of you are again familiar with the greenhouse effect, that if you do not have an atmosphere, then you can find out the temperature of a planet by assuming that whatever radiation is coming in is absorbed by the planet and then it radiates back the same radiation in infrared. So whenever you have this, you assume a balance between the radiation, you could construct this kind of a formula through a black body radiation, and this gives you the temperature of the planet. So I'm not going to too much details here because in the audience there are students from different backgrounds, but the particularly students from physics background would understand that the theory of black body radiation can be applied here. And this, if you do it, a small calculation for each planet like Venus, Earth, and Mars, you would get the temperature of each planet, what it looks like, and we have what has been observed is that most of these temperatures are much lower than what it is. So it is the atmosphere then which forms the temperature of the planet. For example, for Earth, if we did not have the atmosphere, it would have been 25 degrees much colder. And all of you know that it is the greenhouse gas of the atmosphere which forms the temperature by a bit. So this is just to give you a feeling that what are the process, how the sun affects our planet, and how do we take that into account in studying in science. The other aspect is the change of the temperature with height. So this, whatever I've showed you earlier here, is the surface temperature. Okay, so this is the temperature which the entire planet is gaining by interacting with the sun. And that is what you feel immediately near the surface. The next aspect of any planet. So as I said, initially we talked of composition and now we are talking of the temperature. This is a very important characteristic of an atmosphere, that what are the temperatures there. So that was the surface temperature. And then you have a characteristic trend of the temperature with height. And this is what characterizes each atmosphere, and a very important characteristic which will define that atmosphere. It's like, you know, how you define a person. If you take the name of that person, it defines everything for him, that this is that individual. So this is what the temperature vertical structure is, something which characterizes that atmosphere. And in terms again of physics, I'm sorry because I'm bringing a lot of physics, but I'm a physicist. But this is a very general concept of the conservation of energy. All of you must have anyway at some time heard the first law of thermodynamics. And that is very simply and beautifully applied to the atmosphere, to the gases here. And what you get is how the temperature will change with height. And that is something which is, for example, for the Earth's case, you know that the temperature decreases with height in the initial few kilometers, and that's nothing but the lapse rate. It's called the lapse rate. And what I've shown you here is the different lapse rate for different planets. So you can see for Earth and Venus, it is almost similar, and that is why Venus has an atmosphere. It has a very thick atmosphere, and it is very similar to Earth in many respects. And this is one of the similarities, that the lapse rate on Venus is similar to that of Earth, and this is in the lower heights, what I'm talking of. For Mars, it is much slower, the lapse rate, because Mars atmosphere is much thinner to the two other planets. So in a sense, the temperature actually falls off very linearly with altitude. And all of you have actually really experienced that in the Earth. Whenever you go to a mountain, it's much colder. This trend of decrease is linear, given by the first law of thermodynamics. So this is how temperature structure of the planet looks like, of an atmosphere. And typically here what I've shown you is the vertical structure of the temperature. This is called the vertical structure of any atmosphere. This is, as I've said, it characterizes that atmosphere. And so this is what. So if you see something like this, you know that it is Earth's atmosphere. And something like this, it is Venus, and this is Mars. So basically, how does it characterize? You see here the surface temperatures at the ground, and these are the temperatures when the atmosphere is present. Otherwise, they would have been lower. So this is what I showed you earlier. And you can see this characteristic or trend for Earth, where initially the temperature should decrease. This is always a trend. This is a natural trend because the after absorbing the radiation from the sun, due to assuming it as a black body, assuming the planet as a black body, it radiates back in the infrared. And this is the infrared radiation which is absorbed in the atmosphere, and that is what leads to the temperature. So therefore, you are moving away from the source. So this temperature falls naturally, as you know, in the Earth's atmosphere. And then there is an increase in the temperature in the higher layers. This is called something called the stratosphere. Many of you will be familiar. And here it is because there is lots of ozone in the Earth's atmosphere, the temperature increases. And then again, the ozone finishes somewhere here, it decreases. And then again, the natural trend of decrease continues. And then again, you have a very high increase in the thermosphere, very high regions, because of lack of sufficient collisions. The mean free path is very large. But if you see here for Venus and for Mars, you do not have this increase somewhere here because you don't have ozone here. We will come to this topic slightly later, that there is some amount of ozone on Mars, but it is not as sufficient as that on Earth, and there is no ozone layer here which can increase the temperature. So otherwise, you basically the temperature keeps decreasing, and then for much higher altitudes, this increases, just like for Earth. So this is the comparison of different vertical structure of the atmospheres. Next, the important thing which comes in mind if you want to characterize any atmosphere is the physical structure. So these are the three aspects: the composition, the temperature structure, and the physical structure. When we talk of what is the physical structure, basically we are talking of the pressure and the density variations. So now you can, some of you from physics, even chemistry, can correlate this, that since it is a gaseous and it's a gas, you had the temperature, and here we are talking of pressure and density, and all of them are all of them are related through the gas law, the ideal gas law. So this is what is also taken into account for the atmosphere. If you want to characterize its pressure and density and temperature, they all are related to each other. And this is what happens, for example, in the Earth's atmosphere, short variations of pressures and density and temperature, that is what leads to weather phenomena. So in simple terms, if you just look at the laws, you apply simple classical mechanics, and you assume that the pressure gradient forces, they are balanced by the gravitational force in the Earth's in the atmosphere of any planet. So basically, you have an air parcel, and it is, if you look at a parcel of air in the atmosphere anywhere, it is acted on by pressure gradient forces, and the gravity is pulling it down. If you assume that they are in balance, you can do a small calculation, and it will give you a relationship between how the pressure changes with height. Uh, that relationship comes out in terms of the density of the gas of the atmosphere. And if you, this is called the hydrostatic equation, and if you simply integrate this, what it tells you is that the pressure decreases exponentially with height. And again, most of you are familiar with, but this is an important concept, that whenever you characterize any atmosphere, the physical properties, you must understand that the pressure decreases exponentially. And you have experienced this whenever you are flying in an aeroplane, that the flight, whenever you come down, you feel the pressure much more in the lower layers when it's climbing down. And the similar behavior is shown by the density, because pressure and density are related. One of the very important concepts which comes out from such a kind of structure is something called a scale height. And scale height comes out in this process when you are theoretically formulating this. This is the constant H which comes out, which is dependent on the temperature of the planet, of the atmosphere in that region, and the mass of the air molecules, and the two constants, Boltzmann constant. So this is the scale height is nothing but a height in which the pressure or the density will be decreasing by 1 by E. So 1 E fold whenever the pressure and density decreases, that's the scale height. It's sort of a characteristic length scale which characterizes the atmosphere. And in the lower atmosphere, these are the typical values of the scale height. You'll see here again that here it is quite different for Venus and Earth, but Venus and Mars are a bit similar because it's a CO2 dominated atmosphere. And these are the typical temperatures in the lower atmosphere which you would take into account to estimate this scale height. And as all of you know, the acceleration due to gravity is quite different on the three planets. 9.81, for Earth. Venus is a little bit less, at least, but Mars is very less. And so this is what I've told you about. How do you characterize atmosphere? The composition, the temperature, and pressure density, and that is what completely defines an atmosphere. Now, if you go into the details, how would we like to study this? There are, as I said, various processes which are going on. The process which I am now coming to is the interaction of the solar radiation with the atmosphere. And that also gives rise into the temperature structure as we talked to earlier. But this diagram gives you a very nice depiction of the effect which each of this radiation has on the various layers of the Earth's atmosphere, for example. This is the Earth's atmosphere, and this is the troposphere, stratosphere, and up to the exosphere. You see the temperature structure which I have shown you earlier, the decrease and the increase. This is basically affected by different types of radiation. And as I told you earlier, the electromagnetic spectrum is coming with all kinds of radiation, but then X-rays, for example, will be absorbed much higher up in the upper atmosphere, and the UV will come down to the lower atmosphere up to the stratosphere, and then it will be absorbed by ozone, and so this portion gets heated up. Visible light comes much lower up to the lower atmosphere. And here, for example, then it is characterized by the greenhouse gases, and the infrared radiation is trapped here. You have lots of very rapid motions, which we call convection. And so this is there in the Earth's atmosphere. It protects us from X-rays and UV. But what will happen in the other two atmospheres, like in case of Mars, it is very thin. So most of this UV and visible can come even up to the surface. So this is the difference, but this is sort of telling you the kind of processes which we deal with. And then we would like to apply the corresponding physical theories or the physics and study various regions of this atmosphere which give different physical properties due to the interaction of these various wavelengths. So just as a cartoon, I've shown you here that, when you have the different layers in the Earth's atmosphere, the different kind of phenomena exist where you would have balloon flights and airplanes flying here, and then you have stratosphere, mesosphere, you have lots of meteorites coming here, and then the satellites fly much up, higher up. So this is the entire structure is again dictated by the temperature structure, and different kind of phenomena are occurring in each of these layers. For Earth's atmosphere, because all of you are familiar, but certain this kind of phenomena also occur on the other atmospheres, but they do not have, of course, the stratosphere and other divisions. So when we go into the details of interaction of this electromagnetic radiation with the molecules, this gives rise to more detailed phenomena when I was talking of radiative effects, and that is depending on the energy of the photon which comes. So this is the increase in the energy here. And as you can see, if it has not very high energy, the energy of the photon is absorbed. And then slowly to the other end, if it has very high energy, the species will be ionized. So these are the four processes which are dominating in the atmosphere of any planet when the solar radiation interacts. Either it can be absorbed, or it can be scattered, or it would dissociate the molecules themselves to form, so that will sort of disturb the chemistry of that region. Or you could have the ions. It could just knock off the electron and ionize the species. So you also have ions in the atmosphere. So I will come to. So these four processes are dealt with by physical laws, and many of you must have studied this at some scale. The scattering, for example, you must have studied at some level that how scattering occurs, and that is taken into account by in the atmosphere. When we consider scattering by each molecule, then you could have multiple scattering, you could have scattering by one molecule, what are the types of scattering, and all these calculations are taken into account just to see what is the effect of this radiation when it interacts with different layers of the atmosphere. So this whole domain of radiation study, the radiative transfer modeling, so as to say, gives us ultimately the temperature. We can actually simulate the temperature of any planet. And this is something which you most of you must have seen in the Earth's atmosphere. For example, the blue light because of scattering or scattering absorption is the phenomena which leads to the sky being blue, or you can see the red tinge in the atmosphere when the sun sets. So these kind of simple laws can explain this phenomena. But when we study the science of this, when we study the details, we have to go in much more detail to study the at the atomic level how the scattering and absorption is occurring. So this was a brief overview of the various processes and the structure which occurs in the atmosphere of any planet. The next question comes: how do we study them? Earth's atmosphere we have studied through centuries. We know so much about this, but in effect, how do we study them? So first is, of course, in any scientific query, we try to first have observations. Now, if you can appreciate the atmosphere, how would you observe the atmosphere? I again talked about the composition, the the temperature structure, and the physical structure. So these are the three types of quantities you would like to observe. So you would like to observe its concentration, various species, the temperature profile. You would like to detect what is the temperature of the planet at different heights, or what is the pressure and density. And for this, there are either you could have an in situ observations. For example, in the Earth's atmosphere, you could place various instruments. Meteorological instruments are there, which are regularly measuring pressure and temperature and composition. But what about the other planets, the Venus and Mars? So there again, you could either send landers and rovers, which could actually measure them in situ. But these are very difficult missions, as all of you know. But we do still have certain rovers and landers on Mars. For Venus, it is it's a hostile planet, so it's difficult to send such thing. The other then option, very simple, which remains is the orbiters, the satellites. The satellites which orbit around the planet, they can actually observe many of these parameters. And this is the most fascinating part of the whole study, that we have reached such a technology that even for a planet like Mars, where ozone is very small, very minor in quantity compared to Earth, we have been able to map the entire ozone. And this technology comes from very simple principle that you are basically detecting the backscattered radiation from the planet, and that gives you an indication of what the amount of species, the concentration of the species is there. In the sense that, as I said, that ozone will absorb or scatter absorb some kind of UV radiation, which is characteristic. So there is this process of spectroscopy where you know that a species would absorb a certain wavelength or it would emit a certain wavelength. So all these studies reveal that ozone is absorbing in the ultraviolet, and you assume that you construct a model from the radiative transfer, and you assume that if certain amount of ozone is there, it would have absorbed the species in this the radiation by this amount. So whatever is remaining out of after coming out of from that amount of ozone is what you see. So basically, the satellite is observing nothing but the backscattered intensity in UV, and that is the instrument there where it is measuring in the UV, and it is just measuring the amount of radiation. But using a model which you have constructed, which is called an inverse model, you then iterate the whole thing and try to estimate what is the amount of ozone. So this is just an example, but you could do it for other species like methane or CO2 or other species which exist on the planet by just remotely observing. So this is one of the ways you could observe a planet, the composition of the planet. The other thing is, which I said, that the temperature and the pressure structure. So one of the very accurate and very standard experiment is the radio occultation experiment, which various missions have undertaken that. And the concept of this is that when the satellite is orbiting around the planet, it basically sends the signal to Earth where you receive whatever data is being captured by the various instruments on the satellite is given back to the Earth. So in this experiment, what is done is that when the satellite just enters near the atmosphere, the radio frequency is sent back to Earth, to the Earth station, and this is the same frequency which is used to transmit data from the satellite. And this signal suffers some small amount of phase shift due to the medium of atmosphere here. And that phase shift is very, very small in terms of millihertz. And that is what we try to detect at the ground station here. So this is a very simple in the sense that we are using just a radio frequency to measure the very small phase shift which has happened due to the passage of this radio frequency from the atmosphere. And this is called occultation because when the this spacecraft is just about to enter the atmosphere, after that it gets occulted from the line of sight of Earth, and you no longer can see the spacecraft. So only in this amount of time you are able to observe the atmosphere, and then it goes back in the orbit and it goes far from the planet, and then it is in direct in the line of sight of the ground station on Earth, which is the data. Then there is no occultation. So this is comes once in the motion of the satellite, and it is used to uh, the phase shift then which is observed at the ground station. This phase shift, it has a series of physical and mathematical formulations. You construct that, and finally you would get the high profile of various atmospheric parameters like the pressure, the temperature, and the density. And this experiment has been flown on various missions before. And this is what we have proposed for the next missions of India to Mars and Venus, which will study the atmosphere of Mars and Venus, which will we can observe the complete height profile from surface to about 100 kilometers, and we are developing that at PRL. So this is again our observational method remotely to measure the physical characteristic of a atmosphere. And the chemical constituents, as I said, are various spectrometers one can use. There are various ways where you study the composition. Now, apart from observations, the next thing which comes is models. And if you know in science, there are these two areas where theoretically you have to describe a phenomenon, and it should be able to simulate certain quantities which you are being able to observe. And this modeling has been has developed for the Earth's atmosphere to a very advanced stage, where you have now these days models called climate models and weather models, which are now very accurately predicting this phenomenon on Earth. And these have been extended to other planets as well. To start from very simple just concepts that the basic equations used for modeling are very simple. They are basically conserving the mass and momentum, and which gives you the variation of the density with space and time. So actually, you can simulate how the concentrations of various species in the atmosphere are changing with space and time, and you can predict that what will be, for example, how the CO2 will increase in the Earth's atmosphere, how we are impacting that. All these things one can simulate through these theoretical models. The most crucial point to note here is that these processes in all this atmospheric modeling are very simple in terms of physics and chemistry, but their equations which describe these processes are differential equations, and they are all the processes are occurring simultaneously. So they are the differential equations are highly coupled differential equations. So then you have to resort to special numerical techniques and to high performance computations. So they are performed on very large scale computational resources. The next the area which we would like to study by theoretical methods is other radiative processes, as I said. And one of the important things which I said that the photo dissociation occurs. For example, when this solar radiation hits the oxygen molecule, it dissociates into two oxygen atoms, and that is how you form naturally ozone in the atmosphere. So those things are physically taken into account by constructing the rates of these photo dissociation. Then the equations describe how this energy is distributed through processes like scattering and absorption. So radiative processes have also to be taken into account when you consider the entire atmosphere. All the three processes which I showed you earlier, the radiative, chemical, and physical, all have to be coupled to each other. The other class of categories are the general circulation models, where predominantly we would like to study the circulation patterns of the atmosphere. And these are the models which solve the classical mechanics equations, something called fluid dynamics, and they lead to the basic Newton's law, first law of Newton. If you apply it here, it will lead to something called Navier-Stokes equations, and these are then applied in the atmosphere, where the atmosphere is discretized, because as I said, these are numerically solved. All these differential equations are numerically solved. So you discretize the entire space into a 3D grid, and on each grid point you solve these equations, a huge amount of equations, and that will generate the flow of the fluid called atmosphere around the globe, and that is because you're conserving the momentum and the energy. Simple such equations. I mean, simple means the concept is simple, but the equations become complicated, and the whole process is to be solved numerically, and that will give you rise to the winds, and you could generate different. I mean, these models could show you, for example, the circulation between the northern and southern hemisphere, the large scale winds, the trade winds, all these kind of uh, uh, motion have been able to generate by GCMs. And over the past several decades, these GCMs have been developed for the Earth's atmosphere, and now they are being developed. They have also been developed for the other atmospheres like Venus and Mars, and we are working with some of them at PRL. Just to give you a glimpse, all of you may not appreciate such equations, but as I said, the conservation of momentum gives you the motion, and the mass conservation gives you the distribution of the density of species, and the temperature is also can be simulated. The temperature at different points in the atmosphere can be simulated by applying simple conservation of energy through the thermodynamic equations. Again, a different form of the GCM, the basic equations, where you are trying to solve in different coordinates, because the r theta phi coordinates is much more convenient for a planet's atmosphere. Now, coming to very specific planets, for example, the Venus. This is a schematic which gives you an overall overview of what the atmosphere looks like. So the interesting question here, and as of that India is planning for our next mission to Venus, the point here is that there is a thick cloud of haze here, which protects us from seeing the surface. And there are lots of questions related to this cloud layer here, that how it is, what is the composition, and in different layers, what is the composition? You have an upper cloud, you have a lower cloud, and it is made up of predominantly sulfuric acid droplets or aerosols, I will say. And these sulfuric acid aerosols can lead to phenomena, even phenomena like lightning. And how do they condense them? How do they? What is the chemistry here? How there is a lot of convection here in this area. And as you know, there is this problem of super rotation. The atmosphere is rotating much faster than what the planet is itself rotating, and that leads to a lot of dynamics here, and it changes the some part of the chemistry. So this coupled all these phenomena is what scientists are trying to study, different aspects of this, especially the cloud layer is a hot topic where we would like to know exactly what is going on. And this many aspects of this atmosphere, the our next mission to India, we study that. If we come to the atmosphere of Mars, it is again similar to the Earth's atmosphere in one way, that you have seasons here, just like you have on Earth, and that is because there is a tilt in a tilt on the axis of this planet, just like Earth, which is similar, which creates the season. And of course, the gravity is different for these two planets, but the and also the length of the year, because Mars has much more elliptical orbit. But it is the season. Because of the season, there are phenomena like dust storms, which will come to a bit later, and that is what gives rise to the climate of Mars. So as I said, this season is on Mars is coming. It's much more diversified, because the orbit of Mars is much more elliptical, and so different phases of this orbit is shown, and there you would have different seasons. For example, the northern hemisphere here, winter is very short and it is mild, and then you have the southern hemisphere, summer here is brief and warm. And here the southern hemisphere winter is long and very long, but the northern hemisphere is long and cool summer. And this is the time where you would have lots of, whenever the Mars is closer to the sun, you would have lots of dust storms. So this entire orbit is dictating how the seasons would result, and that would decide many of the phenomena in the atmosphere which we are having. The composition we had already talked of earlier, that it's CO2 dominated, but you have these species, there's very trace amount of species. Nitrogen and oxygen are there, but very small amounts. Water vapor is mainly stored in the polar. It is in the form of the water is in the form of vapor here, and it's mainly released from the polar caps. Ozone, as I said, I'll show you a bit later, has been detected fairly well. It's very small, but it has been detected. And methane detection is still a mystery, that we have not permanently seen it, but in trace amounts sporadically. So, and these are, of course, in situ measurements which has been made very accurately. This is something when I talked about the water is present, but in very small amounts. You can see this here again. This is from the Mars color camera on the MOM orbiter, and you can see this streaks of water vapor clouds here on a region called Arsia Mons, which is a high altitude volcanic mountain here. So even these, the clouds of water vapor can be detected. They have been detected by many of the missions which are having cameras and other experiments as well. Now, just like I showed you for Venus, this is an overall summary of what we would like to study in the atmosphere of Mars. In the upper heights, you have the sun, as I said, the solar wind and the sun, which are interacting with the upper atmosphere. And events like the coronal mass ejection, which you would hear in these lectures in your program, and X-rays, they could affect the upper atmosphere to ionization. And this is a typical structure of how the ionosphere looks like. As I said that these radiations produce ions, and ions and electrons are available there. So a typical electron density profile looks like this, and various processes are there which form this ionosphere. So how the solar wind interacts with the upper atmosphere, how the ions are formed, and then once the solar radiation reaches at the lower heights, then there is a lot of dust here. And this is one aspect of the Martian climate which has become very important and which many of us have spent a lot of time in the past few years to study this phenomena, the physics and dynamics of dust in the atmosphere. Most of this is released, and how the solar radiation interacts with this dust. That is one aspect. And then ultimately, how the chemistry of this atmosphere is related to various external forces like solar conditions and the dust itself. So overall, the Mars climate is changing not by man-made processes, but by natural processes where the solar variability will play a very big role. So it's we would also like to see, how the climate is changing in terms of the dust as being a very important component of the climate of Mars. As I said, the ionosphere of Mars, which is in the higher altitudes and affected by solar winds, we have tried to study it as a very important aspect. And this is again a very general structure of the ionosphere. This is nothing, something called the electron density, because when you create an electron is emitted, and the ions and electrons exist in charge neutrality. And so the ionosphere, a region in the atmosphere, is always characterized by the electrons, the density of the electrons. And you can see from the surface to up to 300 kilometers, the ionosphere is there. But different regions of the ionosphere are characterized by different processes. So here the EUV radiation is dominant, which is a major source of ionization. Somewhere here you have X-rays, which are the more major sources. And here you have micrometeorites, which come into the atmosphere of late and form this layer. So the variation of this kind of phenomena, the structure itself, the variation with solar variability, is something which scientists are still studying, and there's a lot of variability and scientific questions which are still pending in such kind of a study. We at PRL have developed a very important model for this complete ionosphere by taking into account various kinds of processes, which I will not go through. But ultimately, we are able to generate a lot of these densities of a lot of ions, at least 30 ions, which we can observe, which we predict are there in the Martian atmosphere. And many of these ions have, for example, been seen to be affected by strong solar events where energy particles enter into the atmosphere of Mars. As I said, that these kind of particles can come lower down to the Martian atmosphere because there is no magnetic field. And so such kind of theoretical studies based on observations also, whatever we can get, are studied by us. The next aspect, as I said, dust storms, which we have spent quite some time to study, are very enigmatic phenomena, and it is very important for the Martian atmosphere. You see here a typical dust storm, how it develops. This is something called the dust opacity. So it's a quantity which tells you how much the radiation attenuates when it travels to. So it's a kind of a length, optical length, dust optical depth, so as to say. And it is sort of a measure of the amount of dust present in the atmosphere, the loading, dust loading, what you can say. And you can see here that the dust loading here is very clear on certain months. This is the Mars picture, the globe picture. And then suddenly somewhere around June or July, this dust starts picking up, and after some time it has covered the entire globe. So all of you know that the Mars is covered by dust. Sometimes the entire planet is covered, and this is a typical, you could say, the global dust storm, which covers the entire planet. And this is again coming back to the motion of Mars. This is because the way the seasons are there. These are some of the seasons where dust storms typically occur, because it is the summer season for the for Mars is closer here to northern summer. Southern summer is there, so you could have large dust storms during this. This is LS is typically the angle between this axis and this rotation which it makes. So it typically characterizes the season. So you start with spring equinox and you move over to the other seasons describing. So this is typically the dust season, where where the LS is about 250 to 300 degrees. And as I said, that the dust amount, I mean, this dust, lot of dust gets loaded into the atmosphere. So how do you actually measure that? It is the optical depth, which I said, and there are various instruments and many missions have gone which have measured these dust optical depth right from 1970s. And so now we have a huge amount of data, and we have looked at that. And if you see here, that these are the typical regions where dust storms would occur, and we try to study through this dust optical depth that what how much dust loading would have happened in different seasons of Mars. And we do observe that this dust storms are typically there every global dust storms every 3 years, where this dust optical depth becomes very high. But and this is, for example, to show you about many years of Mars climatology. So from 1919 to about 14 years, and you have the Martian year. Every 2 Martian years is one Earth year, and sorry, the other way around. And this is Martian years have been labeled from the time where systematic observations of Mars started. And so, for example, 2014 corresponds to Martian year 32. And you see here the optical depth, which is just characterizing dust loading. So, a lot of dust loading happened in 2001. This was again a global dust storm. 2007 was a global dust storm. So, almost every 3 years, we have seen that dust storms cover the entire planet. But the fundamental question which we are trying to answer is that why do these dust storms form? How do they form? And why is it that only certain years they develop into global storms? But otherwise, almost every season you have regional dust storms on Mars, and you have something called dust devils, which I will come. So all this phenomena, understanding that dynamics, how this occur, these are still challenging problems. We have taken into account the interaction of dust with the ions, and developed a very complex chemistry here. And we have shown that this dust can, in fact, destroy the entire ionosphere during very intense dust storm. So, the lots of theoretical calculations have gone into this, and but we have still to make lot of many observations regarding this, because it's difficult to measure when the storms are there. And in fact, models have also shown the impact of dust storms on the circulation. The storms are so intense that it completely changes the circulation patterns on Mars, the wind circulation patterns. And when you want to model such kind of a dust cycle, where the dust is injected into the atmosphere, mixing occurs, and then dust is transported by winds and loaded into the entire atmosphere. This entire process is modeled into the general circulation models, and now we have some level of predictability, but still the prediction of dust activities on Mars is very difficult. One more aspect which I will come to, especially for the Martian atmosphere, is the amount of ozone which is present there. Now, all of you know that in Earth you have very high amounts of ozone, amounting to about 300 to 400 option in it. And 1 Dobson unit is this much amount of ozone present in this small column of 1 centimeter square. And typically, this is just to show you that 300 Dobson unit is amounts to 3 millimeter of ozone and compressed to the STP, standard temperature and pressure. So very high amounts of ozone, all of you know, are present in the Earth's atmosphere. But when you look at Mars, we have taken observations from UV spectrometer, which has mapped the entire ozone on the entire planet. The ozone is hardly 2 to 3 ppm, 2 to 3 Dobson unit compared to 300 Dobson unit on the Earth's atmosphere. But this ozone here is very importantly related to the water vapor cycle on Mars. Water vapor and ozone are very small, very low quantity on Mars, but still it dictates the climate of Mars. And to understand its entire evolution and how it is evolving in different latitudes, longitudes, what are the phenomena which play into account. So these are the kind of science questions we would like to answer through our understanding of basic physics and basic chemistry, and of course using lots of mathematics to solve these equations. So this is what I was saying, that you could do a photochemical modeling of even the Martian atmosphere, where you could, predict what are the kind of loss processes which are occurring in this species. And it is the trace, it is these trace species, water vapor and ozone, which affect the temperature in a very important way. So this kind of modeling is very important, which has been taken from basic principles when we developed it for the Earth's atmosphere. And now coming to a very important aspect, as I said, that this dust storms. Now there are lots of vortices on Mars, and vortices are something which develop when you have high heating at certain locations, and the cold air, the hot air rises, and cold air above the air rushes in. And so therefore it forms something, a helical kind of a structure like vortices, and which are seen on Earth also, like tornadoes, or some kind of something which has vorticity, and these are very predominant on the Martian atmosphere. And whenever these vortex structure, they 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 input the dust here, they take a lot of dust into them, then you can visibly see them as dust devils. So here, for example, you can see some cameras from the landers and rovers on Mars. They have actually seen this dust devils here. And these phenomena are very important, so we try to study them. And there are landers which have this regular pressure measurements. So very short pressure drops, if you observe suddenly, we try to make out that we observed almost like 93 events where convective vortices could have been observed, been detected near the rover, and some of them could carry huge amounts of dust. Now, why this is important is that this will contribute to the dust loading of the atmosphere. So, because the dust is at the surface. So, why is it that the atmosphere has so much dust, so much of dustiness, and that is what you observe from the ground. You can see it's all dust there, it's red completely. So, all this physics, we are trying to understand that how this happens, and to model that, it's quite challenging, because the Navier-Stokes equations are very non-linear, but we have done the modeling of this to some extent, and we have tried to show the structure of these dust devils, how they form, and what amount of dust they can lift, and how much. So that will impact the climate of Mars in a very substantial way. And then we are also modeling these dust storms from the general circulation models, going down to very small scales, and trying to predict such kind of vortices, how they are forming in such regions, which has been possible today due to very large computers being available. Yeah, I would like to just end with a little bit of what kind of problems we have studied in the atmosphere of Earth in terms of modeling. And for Earth, the system of the lower heights and the upper troposphere are coupled to each other. And events like ozone, which are there in the stratosphere, they play a very important role here. And these processes, in terms of the chemistry, the dynamics, radiation, all coupled to each other. and then phenomena at the lower regions which are affecting many of these emissions, and they increase the trace house gases. So these trace gases and the greenhouse gases, they are increasing, and all of these coupled processes, if you model them and try to develop a model, we have done that and tried to compare it with observations. And for example, one can simulate phenomena like the release of high amount of carbon monoxide due to the burning of forest fires over Indonesia. You can see it from observations. Here are the satellite observations, and even the model has been able to predict that. And also, there have been various aircraft observations looking at the pollution of carbon monoxide over various cities. And the models are very accurately being able to predict these uh, pollutions as well. So basically, I've tried to show you that different aspects of the first to explain you in general how we can study the atmosphere through observations, through modeling, and then a few specific examples of a few scientific questions that we would like to study in the atmospheres of different planets. But this entire thing constitutes of something called, all of you know, is the climate system is very complex, and there are various components of this uh, climate system in the atmosphere that we would like to study, and we are doing that continuously with the means of models and through observations. And for other planets, Venus and Mars, these observations are done through satellites, through instruments based on the satellite, many of which you will hear in other lectures. But I wanted to concentrate more on the basic science of how this is done. So thank you very much.